Thinking in terms of lifetimes, the way in which you need to specify lifetime parameters depend on what your function is doing. For example, if we change the implementation of longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. The following code will compile. Here, let me just make this big because now we're just reading things. Here we go. So what they're saying here is that if we were to rewrite longest so that we only return the value of x, we ignored y completely, then it is okay for us to write a lifetime specifier on x, not y, and the return value. The reason for this is y will never be returned. Makes sense? In this example, we specify a lifetime parameter '(a) for the parameter x and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. If the reference returned does not refer to one of the parameters, it must refer to a value created within this function, which would be a dangling reference because the value would go out of scope at the end of the function. Consider this attempted implementation of longest in function that won't compile. So they stated two rules, or I guess two cases, not necessarily rules. One is that you either have to have your return type that has the lifetime parameter. This lifetime parameter has to be equivalent to one of the lifetime parameters on the items that are passed in, whether it be x or y. Or the next scenario is that this lifetime parameter, or this variable itself, is associated with something that's created within this function. However, if you were to create a variable within this function and try to return it as a reference, you would have a dangling reference because this value, like they state here, result, is going to be deallocated at the end of this function block. So regardless of, since you're returning result, a reference to result, this is not going to work. And they show you the error here. Result does not live long enough because it dies at this point. Here, even though we specified a lifetime parameter '(a) for the return type, this implementation will fail to compile because the return value lifetime is not related to the lifetime of the parameters at all. Here's the error message we get. And yada yada yada, borrowed value lives until about here. Borrowed value must be valid for the lifetime of '(a) as defined on the function body. Yeah. The problem is that result goes out of scope and gets cleaned up at the end of the longest function. We're also trying to return a reference to result from the function. There is no way we can specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be to return an own data type rather than a reference, so the calling function is then responsible for cleaning up the value. So what they're saying here is that in this scenario, when we're looking at this code, right, the best thing that we can do to try to fix this is, instead of trying to return a reference to result, we return an own value of result, and then we can continue onward. So this would just become a string instead of a reference to a string, and that would be fine. And technically, since like a reference to a string is copied, that would be perfect. We're just copying over something that's that we can easily pass around. That would work perfectly fine, yeah. Ultimately, lifetime syntax is about connecting the lifetime of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory save operations and disallow operations that would create dangling pointers or otherwise violate memory safety. So they're just reiterating that the lifetime specifiers, as we can look at this thing, and they can put them here too. That example doesn't have it. But what they're saying is that the lifetime specifiers give the compiler enough information to deduce whether or not the code that we've written is memory safe or whether or not it breaks any other rules that they check for at compile time. Lifetime annotations, instruct definitions. So far, we've only defined structs to hold own types. It's possible for structs to hold references, but in that case, we would need to add a lifetime annotation on every reference in the structs definition. Listing 10-25 has a struct named important excerpt that holds a string slice. So we have some code here. Let me just move this over, bring out our editor again, write this out real quick. Ooh, where did it go? Where did it go? Where did it go? Down here. All right. We have struct important, one word, excerpt. We give it a lifetime parameter of a, and part reference a string, comma. All right, so what we see here is that this struct is going to take in a reference and assign it to part. This reference has to live as long as this instance does, or else the instance will try to reference part, but part will be pointing to a reference that has already been deallocated, and that will be a memory issue. So in order to not have a memory issue, this thing right here has to live as long as this instance does, the instance of important excerpt. And then let's finish writing out this example. Let novel equal string from, and I'm just gonna copy the string. Control copy, Control paste. Let first sentence equal novel.split. So we're going to split the string at the first period, or at the period. And then we do a dot next dot expect. Could not find a period. And then next we're saying let I equal important excerpt part first sentence. And check to see if this compiles. It does, so let's go over it real quick, right? So we already went over the struct. The important excerpt takes in a reference to a piece of string and labels it part. We have our novel here, which is just a string. We have our first sentence, which is novel.split. We're splitting it by sentences, by periods. We're calling the dot next on it, which, at least in my mind, is we split the strings and we now have an iterator. We're calling the first instance of that iterator, so dot next, which will give us the, calling dot next on it once will return the first sentence or everything before the first period. And if that did not exist, because I believe dot next is probably returning a result type, then we will do a dot expect. The dot expect, if there is an error, we'll just put this in the error clause. And if there is no error, then it returns the reference or the pointer to that piece of string. What's our first sentence? And to make sure we know explicitly what this is, let's print it out. Print I.part. Let's see what it says. Call me Ismail. And that is before the first period, right there. Cool, so that seems to work. The struct holds one field, part. That holds a string slice, which is a reference. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct so we can use that lifetime parameter in the body of the struct definition. This annotation means an instance of important excerpt cannot outlive the reference it holds in its part field. So basically right here, they're just rehashing what I said earlier, which is that for this struct definition, which they highlighted how it has to be defined in terms of lifetime parameters, this A and this A just denote the constraint that the instance of important excerpt must outlive or live as long as the reference that it's using within its variables. So part has to live as long or longer than the instance of important excerpt, which we have our instance here, I, and part has to live longer than I, or as long as I. The main function here creates an instance of the important excerpt struct that holds a reference to the first sentence of the string owned by the variable novel. The data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after important excerpt goes out of scope. So the reference in the important excerpt instance is valid. Okay, so what they're saying here is that the part, which is first sentence, a reference to first sentence is a reference to novel. So what that means is that this thing has to live as long as or longer than this instance, which is I. To see that it does, we note that first sentence comes from novel. Novel dies here, or gets deallocated here. I also dies here. So in terms of lifetimes, they are equivalent. Because they are equivalent, we can ensure that part exists for the entirety of this instance, which is important excerpt. Next, lifetime elisions. You've learned that every reference, let me make this bigger, hold on. Lifetime elisions. You've learned that every reference has a lifetime and that you need to specify lifetime parameters for functions or structs that use references. However, in chapter 4, we had a function in listing 4-9, which is shown again in listing 10-26, that compiled without lifetime annotations. So basically what they're saying here is that prior to this section, with this paragraph right here, we've kind of implied that anytime you have a function that takes in references and spits out references, we need to write a lifetime parameter there, like it has to be in the function name. However, they're pointing out that in chapter 4 we wrote a function like this thing right here, and it doesn't have it, even though it takes an input lifetime and has an output lifetime. So what's going on? And to be clear, let's go over what this first word does. First word, we take in a reference to a string, we turn that reference into bytes, we then loop over those bytes, take the index while we're looping over them, we take the index while we're looping over them, and if we see a byte that's equivalent to a empty string, we then return a slice of bytes from 0, the start, to that empty string, not including that empty string. And that will be the first word, or all the letters / words before the space. And if you don't see an empty string, you go all the way to the end and just return the whole thing. Anyway, the reason this function compiles without lifetime annotations is historical. In early versions, pre 1.0 of Rust, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have been written like this. So back in the day, prior to Rust 1.0, this is how that function signature would have been written. We would have the lifetime here for the function, and would have been like s is equal to a, and the return type also has a lifetime of a. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations over and over in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code so the borrow checker could infer the lifetimes in these situations and wouldn't need explicit annotations. So here they're saying that the reason why we can get away with writing this now is because over the course of time, the Rust team and Rust programs have been writing annotations in certain situations that we can deterministically predict, or we can look at the code and based on a certain number of rules, we can infer, well, not necessarily infer, but we can figure out what the lifetimes should be. Yeah, so they put those rules into the compiler's code, and now the compiler can check those rules, and if they apply, we don't have to write them. So seemingly in this situation, those rules applied, and thus we got away with writing this. This piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added to the compiler. In the future, even fewer lifetime annotations might be required. So the reason why this is important to know is that in the future, they might figure out other patterns that could be added to the compiler so that we, as programmers, can write less lifetime annotations. Okay, noted. The patterns programmed into Rust analysis of references are called the lifetime elision rules. These aren't rules for programmers to follow. They're a set of particular cases that the compiler will consider, and if your code fits these cases, you don't need to write the lifetimes explicitly. So it's just what we set up there. The elision rules don't provide full inference. If Rust deterministically applies the rules, but there is still ambiguity as to what lifetimes the references have, the compiler won't guess what the lifetimes of the remaining references should be. In this case, instead of guessing, the compiler will give you an error that you can resolve by adding the lifetime annotations that specify how the references relate to each other. So here they're saying that if the rules are applied, like these rules that they haven't mentioned to us yet, if they're applied and post them being applied, there's still some ambiguity as to what a lifetime parameter could be for one of these variables, then the compiler is going to throw an error and tell us that we need to specify the lifetime parameters. Seems legit. Lifetimes on functions or method parameters are called input lifetimes, and lifetimes on return values are called output lifetimes. The compiler uses 3 rules to figure out what lifetime references have when there aren't explicit annotations. The first rule applies to input lifetimes. The second and third rule applies to output lifetimes. If the compiler gets to the end of the 3 rules and there is still references for which it can't figure out lifetimes, the compiler will stop with an error. These rules apply to function definitions as well as implementation blocks. Okay, so that's rehashing what they set up there, but now we know there are 3 explicit rules. The first rule is that each parameter that is a reference gets its own lifetime parameter. In other words, a function with 1 parameter gets 1 lifetime parameter. Here's an example. Fo only has an x, so a is applied to x, and it only has 1 lifetime parameter, which is a. A function with 2 parameters gets 2 separate lifetime parameters. I said foo. Function foo with x and y, well, that's 2 parameters, so x is going to get its own lifetime, a, and y is going to get its own lifetime parameter, which is going to be b, and so on. The second rule is that if there is exactly 1 input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Ah, I see. So in the first example, we had 1 input lifetime parameter, or we have x, right? And by the first rule, x is going to have a lifetime parameter of a. And now, based on the second rule, if there is only 1 input lifetime parameter, then all the output lifetime parameters are going to be equivalent to that 1. So this is going to get assigned the lifetime parameter of a. They have parameters plural here, so seemingly if there was multiple output lifetime parameters, then they will all be assigned to a. The third rule is if there are multiple input lifetime parameters, but one of them is self or a mutated version of self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes methods much nicer to read and write because fewer symbols are necessary. So for the third one, they're saying, in terms of methods, if there is a self in the input parameters, then all the output parameters are going to have a lifetime equivalent to that of self, which makes sense because that means that all of the output parameters are going to live as long as the instance of self will, which is necessary in order for an instance to use these parameters. Let's pretend we're the compiler. We'll apply these rules to figure out what the lifetimes of the references in the signature of the first word function in listing 10-22 are. The signature starts without any lifetime associated with the reference. Here this is going over some applying the rules, but we'll see how it goes. So we have first word, right? No lifetime parameter references. And if we were the compiler, first we do rule 1. Then the compiler applies rule 1, which specifies that each parameter gets its own lifetime. So we're going to write an A here, and that the rule 1 only applies to input parameters. So right here we see the output of that. We have the lifetime parameter of A here and A here. Next, we should be able to apply rule 2 because there is only one input lifetime, one input lifetime parameter. And that's exactly what they say here. Okay. The second rule applies because there is exactly one input lifetime. The second rule specifies that the lifetime of the one input parameter gets assigned to the output lifetime. So the signature is now this. And here we go. A's got assigned to the output lifetime parameter. And now that every parameter has a lifetime, we're done. The compiler can say, this is good. Now all the references in this function signature have lifetimes, and the compiler can continue its analysis without needing the programmer to annotate the lifetimes in this function signature. Let's look at another example, this time using the longest function that had no lifetime parameters when we started working with it in listing 10-21. Here's how it first looked. Longest has 2 lifetime inputs and 1 lifetime output, a lifetime output parameter. So we apply the first rule, and the first rule states that every input lifetime parameter gets its own unique lifetime parameter. So X is going to have A, Y is going to have B, and they're defined here. We cannot apply the second rule because we have more than one input lifetime parameter. So then we try to apply the third rule. The third rule says that if we have a reference to self, then the output lifetime parameters all have a lifetime parameter that is equivalent to self, the one that self has, but that doesn't exist here. So that is rule 1, 2, and 3, and then at the end of the third rule, we still don't have a lifetime parameter for this, and thus the compiler should raise an error. And let's see how they state it. You can see that the second rule doesn't apply because there is more than one input lifetime. Yeah, we stated that, yes. The third rule doesn't apply either because longest is a function rather than a method, so none of the parameters are self. After working through all 3 rules, we still haven't figured out what the return type lifetime is. This is why we got an error trying to compile the code in listing 10-21. The compiler worked through the lifetime and listen rules, but still couldn't figure out all the lifetimes of the references in the signature. That makes sense. Because the third rule really only applies in method signatures, we'll look at lifetimes in that context next to see why the third rule means we don't have to annotate lifetimes in method signatures very often. Okay. And coming closer to the end of this section, lifetime annotations and method definitions. When we implement methods on a struct with lifetimes, we use the same syntax as that of a generic type parameter shown in listing 10-11. Where we declare and use the lifetime parameters depend on whether they're related to the struct fields or the method parameters and return values. Lifetime names for struct fields always need to be declared after the implementation keyword, and then use after the struct's name, because those lifetimes are part of the struct type. All right, so let's look at this and this, right? These two paragraphs. The first one stated that the syntax for declaring a lifetime parameter is the same syntax as declaring a generic type parameter. And you have an example down here where we have the angle bracket, and then we have, instead of the generic T, we have the apostrophe A. And we also put it after the struct name. Same way we do with generic types. And then the second line here was the second part I just mentioned, was that this has to go after implementation and this has to go after the name. And this is tying the implementation to the instance of the struct. In method signatures inside the implementation block, references might be tied to the lifetime of references in the struct fields, or they might be independent. In addition, the lifetime and listen rules often make it so that the lifetime annotations aren't necessary in method signatures. Let's look at some examples using the struct name import excerpt that we define in listing 10-25. First, we'll use a method name level whose only parameter is a reference to self and whose return value is an I32, which is not a reference to anything. So this is probably right out. Let me just move this over. Get back to where I was. Here we go. And editors here. Yeah, I'm writing out level. There we go. Implementation. Have lifetime parameters. Implementation block for this guy. Give it its lifetime parameter. And in here, this implementation block, we're going to write a function called level, if I can spell it correctly. And it's going to have a reference to self, and it's going to return an I32, which doesn't reference anything, and just going to be hard-coded, right? So that's the syntax. But this next line is which is curious to me. What it says here is that the lifetime parameter declaration after implementation and its use after the type name are required, but we're not required to annotate the lifetime of the reference to the self because of the first listen rule. So the annotation for a lifetime annotation does not need to be annotated there because of rule 1. If there is only one input lifetime parameter, then it's going to get assigned a unique one, and then in rule 2 doesn't apply because this is not a reference. This is just 3 being passed. So rule 1, and after rule 1, all of the things that should have a lifetime parameter do. We're good. But what's curious to me is saying that this is mandatory, this part. So let's just make sure it's mandatory. And we got an error. Expected lifetime parameter. Okay. So the reason why I believe it's mandatory is because up here when we declared the struct, we had a lifetime parameter. If that wasn't there, I don't think this would be mandatory, but that's the section we're going over. Let's keep it. And I'm not sure if we need the editor anymore. Let me just move this over. Here is an example where the third lifetime listen rule applies. So they created a new function, right? Announce and return part. Okay. We have a input parameter that's a reference to self, and we have a second input parameter that's just there. And then we return a reference, which is going to be an output lifetime parameter. So for rule 1, this is going to get its own. So let's call this lifetime A. This is going to get its own. Let's call this lifetime B. Rule 2 doesn't apply because there are more than one input lifetime parameter. There's 2 in this case. But rule 3 applies because one of the input parameters is self, which means this is a method. And rule 3 states that because one of the input methods is self, all of the output parameters are going to have a lifetime equivalent to self. And at that point in time, every lifetime parameter, whether it be input or output, has a lifetime parameter associated with it. And thus, we don't need to explicitly write it. Let's see what they wrote. There are 2 input lifetimes. So Rust applies the first lifetime eliciting rule and gives both self and announcement their own lifetimes, like we stated, A and B. Then because one of the parameters is self, the return type gets the lifetime of self, and all lifetimes have been accounted for. Good job. All right, next we have the static lifetime. One special lifetime we need to discuss is static, which means that this reference can live for the entire duration of the program. All string literals have the static lifetime, which we can annotate as follows. So let s, and then here's the static lifetime, string, and then here's the string literal. And I did mention this earlier when we were doing the examples. Yeah, so this is it. This is the static lifetime, and all string literals have it, at least according to the statement. The text of this string is stored directly in the program's binary, which is always available. Therefore, the lifetime of all string literals is static. Makes sense. You might see suggestions to use the static lifetime in error messages, but before you specify static as the lifetime for a reference, think about whether the reference you have actually lives the entire lifetime of your program or not. You might consider whether you want it to live that long, even if it could. Most of the time, the problem results from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. So what they're saying here, there are going to be times in the future in our Rust career where the compiler is going to suggest that we use a static lifetime. And every time we see that suggestion, we should question it, because that could mean there is a bigger problem or a more root cause in our code that's causing this to be suggested. And that problem could be like the mixing of lifetimes improperly, mismatch of lifetimes, so they stay here, or we created a dangling reference by accident. In any case, we should always question that suggestion and based on the scenario, write our code appropriately or correct that code appropriately. Moving on. Generic type parameters, trait bounds, and lifetimes together. Let's mush all these things together. So let's briefly look at the syntax of specifying generic type parameters, trait bounds, and lifetimes all in one function. Okay, take a sip of water. So here we use the standard library format display. This is a trait. Noted. We have our function, longest with an announcement. We have our lifetime parameter, which is A. We have our generic parameter, which is T. X, which is a reference string, or string reference, is going to have a lifetime of A. Y, which is a string reference, is going to have a lifetime of A. And they added a parameter called AND, which is going to be the generic type T. And we're returning a string reference that has a lifetime of A. And then we have the trait constraint where T will implement the display trait. Okay, and then we see down here, print announcement and. Since and, we're able to print and because and implements the display trait, which makes sense. And then here is where we have the need for our lifetimes, which is similar to what we wrote up there when we wrote the original longest. If the length of x is greater than length of y, return x, else return y. Understood? This is just an example of using all three together. The lifetime parameters, the generic types, and the trait bounds. This is the longest function from listing 10-22 that returns the longer of two string slices. But now it has an extra parameter named and of the generic type T, which can be filled in by any type that implements the display trait as specified by the where clause. This extra parameter will be printed before the function compares the lengths of the string slices, which is why the display trait bound is necessary. Because lifetimes are a type of generic, the declarations of the lifetime parameter, '(a), and the generic type parameter, T, go in the same list inside the angle brackets after the function name. Yeah, just rehashing what I said. Last, the summary. Summary. We covered a lot in this chapter. Now that you know about generic type parameters, traits, and trait bounds, and generic lifetime parameters, you're ready to write code without repetition that works in many different situations. Generic type parameters let you apply the code to different types. Trait and trait bounds ensure that even though the types are generic, they'll have the behavior the code needs. You learned how to use lifetime annotations to ensure that this flexible code won't have any dangling references. And all of this analysis happens at compile time, which doesn't affect runtime performance. Believe it or not, there is much more to learn on the topics we discuss in this chapter. Chapter 17 discusses trait objects, which are another way to use traits. Chapter 19 covers more complex scenarios involving lifetime annotations, as well as some advanced type system features. But next, you'll learn how to write tests in Rust, so you can make sure your code is working the way it should. That was kind of depressing. So basically they said that we've learned a lot, we've grown, we understand Rust a little bit more. However, in chapter 17, we're going to go over trait objects because there are more things about traits that we just haven't learned yet. And in chapter 19, we're going to cover more complex scenarios dealing with lifetime annotations, i.e., there's still a lot to learn about these topics. But the next section, or the next chapter, is going to be on tests, and I'm looking forward to writing tests because I'm a big fan of tests. Tests are what I live my life by in terms of programming. Well, with that being said, that's the end of this video. Hope you enjoyed it. Hope it was entertaining. Hope it was useful. Peace.